Hi everyone, welcome to Orgo Essentials, not your basic organic chemistry tutorial, Episode 2. In this episode, I'll be discussing what Lewis structures are, why they're important to organic chemistry, and how to draw them. Let's get started. Lewis structures are drawings that can help show the two-dimensional shape of a molecule or atom. These drawings can be super complicated or very simple. They were invented and named after Gilbert Lewis, an American chemist who first proposed the idea that electrons travel in pairs. Lewis structures can be used to figure out a molecule's general structure, geometry, hybridization, and reactivity. As you can tell, they're very significant in organic chemistry, which revolves around predicting reactions. Here is a Lewis structure of one of the simplest organic molecules, methane, or CH4. Remember that valence electrons are the electrons in an atom's outermost energy level. These are the electrons that bond and participate in reactions. In covalent bonds, they are shared between two atoms. Valence electrons are represented in Lewis structures as dots and dashes. Dots for valence electrons that don't bond, and dashes for electron pairs that do bond. As you can see, methane has 4 bonding electron pairs, for a total of 8 valence electrons being shared between hydrogen atoms and that central carbon atom. Let's go through the steps of drawing a Lewis structure. We'll try to replicate this one of methane. Step 1 is always to count the total number of valence electrons present in the molecule. Remember that the number of valence electrons carried by each atom can be found using the periodic table. Carbon is in family 4A, so it carries 4 valence electrons. Hydrogen is in family 1A, so each hydrogen atom carries 1 valence electron. 4 plus 4 times 1 gives us a total of 8. This is the number of valence electrons we'll use to draw our Lewis structure. We cannot go above or below this total. Step 2 is to draw the molecular skeleton. This means that we must arrange the atoms, represented by the atomic symbols from the periodic table. There are a couple of guidelines for this step. First of all, molecules are usually symmetrical and as spread out as possible. This means that methane won't have all the hydrogens all to one side, like this. It will have them spread out evenly, like this. Another general rule is that hydrogen and halogen atoms, the atoms in family 7A, do not usually form more than one bond. Hydrogen can't be in the center of methane, forming multiple bonds, like this. It can only ever be on the outside. Finally, remember to never draw a ring unless the molecule has the prefix cyclo. Methane does not, so it cannot be a ring. This is the molecular skeleton for methane. The third and final step is to fill in the bonds and check the electrons. When we fill in bonds, we draw lines connecting the atoms. Each dash represents 2 electrons. In this case, filling in the bonds is easy. We simply draw lines connecting each hydrogen atom to the central carbon atom. Now, we check to make sure that we have the correct number of electrons in the molecule, and that each atom has a completely filled octet. Remember that every atom in a stable molecule should have 8 electrons surrounding it. There are some exceptions to this rule. For example, hydrogen only gets 2 electrons to be satisfied, but we'll get into that with some later examples. 2 plus 2 plus 2 plus 2 is 8. Our original valence electron total, so we're good there. Carbon has 8 electrons around it, 2, 2, 2, and 2, so it's stable. Each hydrogen atom has 2, so they're stable too. We just drew a Lewis structure. Let's do some more examples. Feel free to pause this video and draw on your own before checking your answers. Ethanol, an alcohol found in automobile gasoline, has the molecular formula C2H6O. Like with methane, Our first step is to count the total number of valence electrons present. Each carbon atom has 4, each hydrogen atom has 1, and the oxygen atom has 6, which we know from the periodic table. This gives us a total of 20 valence electrons. Now we draw the molecular skeleton, keeping in mind that hydrogen cannot form more than one bond. In many cases, the molecular formula is written to help you draw this skeleton. We know that oxygen will be on the outside, after the carbon atoms. The molecular skeleton ends up looking like this. Now we can fill in the bonds in this basic structure. When we do this, connecting all the atoms together, we use up 16 electrons. See these 8 bonds. This means that we have 4 valence electrons left to complete octets. Fortunately, every atom already has a complete octet, except for oxygen, which needs exactly 4 more electrons. We draw these in as non-bonding electrons, called lone pairs. Let's double-check this Lewis structure. Each hydrogen atom has 2 electrons around it. The rest of the atoms have 8. We just drew another Lewis structure. Let's do another simple organic molecule. Propane, C3H8. The total number of valence electrons present will be 3 times 4 for the carbon atoms, plus 8 times 1 for the hydrogen atoms, for a total of 20. To draw the molecular skeleton, we have to remember that hydrogens can't form more than one bond, so the carbon atoms must be inside. We end up with this. When we fill up the bonds, we end up with something that looks like this. Let's count our electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Since we don't have any spare electrons, we know that there are no lone pairs. This is confirmed when we double-check the octets. Each hydrogen has 2 around it, and each carbon atom has 8. This is correct. Next, let's draw the Lewis structure for a molecule that we all know and love, water, or H2O. The total valence electron count will be 1 for each hydrogen atom, plus 6 from the oxygen atom, for a grand total of 8 valence electrons. Next, we'll draw the molecular skeleton. Remember, most molecules are as symmetrical as possible, and hydrogen atoms can't form more than one bond. This means that the 2 hydrogen atoms will be on the outside, and the oxygen will be in the middle, like this. Now, we fill in the skeleton with 2 single bonds, connecting the hydrogens to the oxygen atom. This uses up 4 valence electrons, so we have 4 left. Like with ethanol, these electrons become lone pairs around oxygen, like this. When we check for octets, we see that each hydrogen is happy with 2 electrons, and the oxygen now has a total of 8 electrons around it. Finished. Let's do one more like this. The next molecule, dimethyl ether, CH3, CH2, O, CH2, CH3, has a few more atoms than the other ones we've looked at, but the concepts are still the same. First, we have to count the total number of valence electrons present in the molecule. There are 4 carbon atoms, each contributing 4 valence electrons, plus 10 hydrogen atoms with 1 electron each, plus 1 oxygen atom with 6 valence electrons. This all adds up to 32 valence electrons. Next, let's draw the molecular skeleton. This might seem impossible, but remember that the molecular formula is often written to help you out. We know that there will be 2 carbon atoms with hydrogen surrounding them, then an oxygen atom, then 2 more carbon atoms with hydrogens. Even if we had the molecular formula written differently, we just have to remember, symmetry is always key, so we end up with this. Now we have to fill in all of these single bonds. By doing this, we use up 28 electrons. We only have 4 electrons left to place. When we look for uncompleted octets, we can see fairly quickly that oxygen needs these 4 leftover electrons. so we can draw them in as lone pairs. Double check that each atom has a completed octet, and we're done. Hopefully, you're starting to get the hang of Lewis structures like these. If you have any questions about Lewis structures, feel free to email me or comment down below. The next video will be about Lewis structures with multiple bonds. I'll see you then.